Welcome to the Semi-Learned Lectures. We are about to embark on a 3-part series, Adventures in Op-Amps. In Part 1, we will learn how to make various types of amplifiers using op-amps, learning how to solve the basic op-amp problems along the way. We will then learn how to solve many more types of op-amp problems that we may encounter in quizzes and tests. The third and final part is for the curious ones among us, who want to examine the inner workings of op-amps and to understand how they operate. Jumping straight into part 1 of our adventure, where we will explore in 4 mini episodes how op-amps are used to make practical amplifiers. The first episode deals with the 2 things that op-amps seem to have too much of: more inputs than one expects and a ridiculously high amplification gain. Conceptually, amplifiers are simple electronic circuits that take in a very faint input electrical signal, like the triangle wave we have here, and amplify it, producing a large output signal. There are 2 simple rules to this amplification process. Rule number 1 is that the output signal is identical in shape to the input signal. Rule number 2 is that the output signal has to be much larger in magnitude compared to the input signal. So the shape of the output waveform remains triangular, just a much larger triangle when compared to the input signal. To amplify the input signal, the amplifier requires electrical power, which we supply to it using 2 fixed level voltages: the positive supply voltage, Vs+, and the negative supply voltage, Vs-. The op-amp is the fundamental building block for almost all modern electronic amplifiers. So you would think that there exists a wealth of good explanations on how op-amps work. But newcomers to op-amps are faced with many non-intuitive concepts. To start with, instead of having a single input for our faint signal, the op-amp seems to have 2 input signals and not 1. They are both called V sub I, implying that they both can be used for inputs. But the plus and minus signs attached to them imply that we need a positive and negative signal as inputs to the amplifier. This begs the common question of how should we connect the incoming faint input signal to the op-amp? And as we learn more about op-amps, we are confronted by more confusing concepts like the infinite gain that the op-amps possess and the often misunderstood virtual short circuit that sometimes exists between the 2 input terminals. And then we have to deal with the seemingly contradictory concepts like the 2 inputs having almost infinite input resistance, but at the same time displaying a virtual short circuit between them. And finally, there is the 0 output resistance, to contrast with the infinite input resistance. The unvarnished truth is that op-amps are one of the most complex topics in electronics. But fear not. In part 1 of this series, we will simplify these complex concepts so that folks who are new to op-amps can understand how these devices work. In part 2 of this series, we will use our newly found understanding to solve typical op-amp problems so that we can hopefully get decent marks in op-amp exams and quizzes. In the final part of this series, we will explore key practical engineering concepts that drive the internal design of both op-amps and amplifiers that are based on op-amps. The topics contained in the final part are seldomly discussed in electronics courses, but they cover practical engineering considerations that are often encountered when designing electronic and computer products. Let's first address the input pins question. It turns out that while amplifiers indeed are designed to amplify a single input signal, the op-amps which are used to create these amplifiers are designed to amplify the difference between the 2 signals. When 2 signals are applied to the two input terminals of an op-amp, the first thing that the op-amp will do is to subtract the signal that appears on the negative input terminal from the signal that appears on the positive input terminal. And it is that difference between the two signals that is then amplified inside the op-amp. In textbooks, the negative input terminal is usually called the inverting terminal, while the positive input terminal is called the non-inverting terminal. But we prefer to call them the negative and positive input terminals to better match the symbol of V input minus and V input plus that are often used in op-amp circuits. There are several good reasons why the designers of op-amps decided to amplify the difference between two signals instead of amplifying a single input signal. And we will explore these reasons gradually as we make our way through the 3 parts of the series. But for now, let's think about how to connect the faint input signal to the op-amp inputs. If we were to connect the faint input signal to the positive input of the terminal of the op-amp and at the same time tie the negative input terminal to ground, what would happen? Since the ground is always at 0 volts, the faint signal is not modified by the subtraction and shows up unaltered at the output of the subtractor. Now that signal, which is identical to our faint input signal, is ready to be amplified. Amplification is equivalent to multiplying the signal after the subtraction by a gain factor to produce the resulting output signal. Okay, this seems like a plausible approach to using the op-amp as an amplifier for an input signal. But when we look at the usual values for the gain factor, we soon find a problem that would upset this plausible approach. So what would be a good value for the gain factor of an op-amp? One would think that the gain factor in the order of 10, 100, or even 1,000 would be sufficient. This way, if the peak-to-peak amplitude of our input signal was a tiny 2 millivolts, then a very decent amplification gain factor of 1,000 would boost it to a respectable peak-to-peak range of 2 volts. But instead of making the gain a reasonable number like 1,000, engineers that design op-amps usually make the op-amp with massive gain factors like 100,000 and often even more than that. Let's park the question of why the op-amp gain is so high for now, and instead let's first focus on what would happen if our 2 millivolt signal was to encounter a 100,000 gain factor in an op-amp. Well, the 2 millivolt signal times 100,000 would theoretically give us a signal whose peak-to-peak amplitude is 200 volts. And that massive output voltage would be due to a very, very small 2 millivolt input signal. What if the input was a more respectable 20 millivolt? In that case, the theoretical amplitude of the output signal would be an even more dangerous 2,000 volts. Of course, all these are just theoretical calculations. In reality, the output of the op-amp can never reach anywhere near these high voltages because the maximum voltage level that an op-amp can ever produce is capped by the level of the supply voltages that we provide to run the op-amp internal circuits. These voltages are usually about plus 15 volts and minus 15 volts. And so the maximum voltage an op-amp can produce is just a tad less than 15 volts in the positive side and a tad above minus 15 volts on the negative side. Let's see how the limited range of the supply voltage impacts the shape of the output signal. Again, let's assume that the gain is 100,000, which is not an outrageous number for modern op-amps. Then the theoretical output signal would go to a peak-to-peak voltage of 200 volts. But in reality, this will not happen. Instead, whenever the value of the input signal times the gain results in a number that is within the range of plus to minus 15 volts, the op-amp will produce a nicely amplified version of that part of the signal. However, if there are any values of the input signal that when multiplied by the gain results in a number that is larger than plus 15 volts, then the op-amp will just produce the fixed voltage that is just below 15 volts. And the same thing will happen if the input voltage times the gain results in a number that is lower than minus 15 volts. In that case, the op-amp will just produce an output voltage near minus 15 volts. The problem we now see is that the output signal is clipped, and yes, that is a technical term, at plus and minus 15 volts. That means this configuration of the op-amp, coupled with the very high gain, will break the first and most important rule of amplifiers, which stipulates that the output signal has to have the exact same shape as the input signal. So this arrangement of an op-amp with a signal on the positive input and the ground on the negative input will not give us a good amplifier due to the very high gain of the op-amp. We need to find another way to use the op-amp as an amplifier. But before we do that, we need to understand why the op-amp gain is made to be so high and how to use that high gain. That will be the topic of the episode number 2 in the first part of our adventure: how to harness the high amplification gain of the op-amps